All right. Nobody has shown up for class. And even though it means I might feel a little bit silly doing so, I'm going to go ahead and give the lecture, cover the material. So hopefully somebody will be able to at least not fall behind by following the lecture on Canvas. When last we met, we talked about permutations and combinations. If you have a set of n objects, every possible specific order you can arrange them in is a permutation. A permutation differs from a combination in that in a combination, if you have the same objects but they're listed in a different order, that is while that would be a different permutation, it is in fact one and only one combination. Here's the example. You have A, B, C, and D. Well, I'm going to need more space than that, so write these larger, make more room. You've got A, B, C, and D. If you choose A first, then you can choose either B, C, or D second. If you choose B first, you can choose A, C, or D second. If you choose C first, you can choose A, B, or D second. And if you choose D first, you can choose A, B, or C second. If you then choose B, then you can choose either C or D. If you choose C, then you can choose B or D. And if you choose D, you can choose B or C. And having chosen A, B, and C, that leaves only D. A, B, and D leaves only C. A, C, and B leaves only D. A, C, and D leaves only B. A, D, and B leaves only C. A, D, and C leaves only B. Those are all of your possible permutations. You'll notice here, you have chosen A, C, B, and D. And here you've chosen A, C, D, and B. These are simply two permutations of the same combination. And last time we looked at the counting rule for permutations, and we found that you were going to make a Fussell. Excellent. I was going ahead and recording the lecture. Just recapping what we've already covered, the difference between a permutation and a combination. And as review, the notation NPR means using R objects out of a set of N objects, you can produce N factorial divided by N minus R factorial permutations. Now, given the same set of N objects and using the same number of R objects from that set, same subset R, you can produce NCR combinations as N factorial divided by N minus R factorial times R factorial, which is really just the total number of permutations divided by R factorial, where the R factorial in the denominator basically divides out all of the duplicate permutations of the same combination. And that is where we left off. The example they give in the book is an advertiser executive must select 3 different photographs for an advertising flyer. If he has 10 different photographs that can be used, how many ways can he select 3 of them? In other words, how many combinations of 3 can he select out of 10 different photographs? And the answer is 10C3, which is 10 factorial divided by 10 minus 3 factorial times 3 factorial. Which is 10 factorial over 7 factorial times 3 factorial. And they go through and do the arithmetic, and they say that the result comes out to 120 possible combinations of 3 photographs out of 10. Pardon me. And that is where we left off. There is one more example they give. It says, in a club there are 7 women and 5 men. They are going to put together a committee of 3 women and 2 men. So how many different possibilities are there? Well, there are, out of 7 women, they're going to choose 3. So that would be 7C3 women. And out of 5 men, they're going to choose 2. That would be 5C2. Now, what does this represent? We're taking the product. This is the possible combinations of women and this is the possible combinations of men. Back up and look at our counting rules. Remember our addition rules for probability? If they are mutually exclusive, tiny papers. Multiplication rules and conditional probabilities. Looking for the probability of selecting what? Let's just look at this. We're looking for the total possible combinations. Remember, you start off with this many possible combinations of women, right? And that works out to what? 7C3 would be 7 factorial over 7 minus 3 factorial times 3 factorial. Do they give us that number? They don't. You got your calculator out? No, here. Let's use this one. I got mine out. So we've got 7 factorial is 5,040. Divided by, what's 7 minus 3 factorial? 4 factorial times 3 factorial. And 3 factorial is? Gotta bet you do. Can't believe you don't. That is just unbelievable. Look in your instructions and see if it tells you in there somewhere that it lists it as a secondary function. Like maybe second function of the number 3 or something. Anyway, 3 times 2 is 6 times 1, so that's 24 times 6. Is 144. Which means there are 35 possible combinations of women that they can choose for this committee. This is the combination formula here, yeah. So they can choose 35 women for this committee. Here, they can choose 5 factorial divided by 5 minus 2 is 3 factorial times 2 factorial. And that is equal to 5 factorial is 120 divided by 3 factorial is 3 times 2 is 6 times 1 is 6. And 2 factorial is 2. So that's 120 divided by 12, which would equal 10, right? Yep. So there are 35 possible combinations of women they can choose and 10 possible combinations of men that they can choose. That means that for every one of these 35 possible combinations, they can associate any one of these 10 possible combinations, which means that the total number of combinations they can choose is 350. Is that what the book got? It is. You don't have a factorial key. Let me see that. I truly cannot believe that. Probability. No, but look what you've got here. You've got all these stat functions. And by golly, there is no mention of a factorial function in there anywhere. That's kind of surprising. That's actually kind of shocking. They've got the combination rule formula programmed in for you, but they don't have the permutation rule. Okay, well, that is where we left off last time, with a little bit more explanation on the whole probability combination versus permutation rule. And basically, the combination rule is just the permutation rule with all the duplicates divided out, canceled out. Now, let's talk about combining probability and counting rules. Section 4.5. You can combine them in order to solve some, quite a few interesting and germane problems. Let's go through some of these examples. In particular, let's go through the first one and the second one, 450 and 451. 4 aces and defective transistors. I want to find the probability. You ever play poker? You ever wonder how they calculate all those probabilities? What's the likelihood of this happening or that happening? Well, that's what we're going to look at right now. What are the probability of getting 4 aces if you draw 5 cards randomly out of a deck? And we're assuming that the first 5 off the top, or every other or every 5th card off the top is going to be random if the cards are adequately shuffled. Which actually is a pretty good example. I should have thought of this the other day when I was talking about the difference between classical probability and empirical probability. Classical probability assumes that every outcome is equally likely. Well, in the case of a shuffled card deck, that means it's assuming that the probability of drawing any card is equal if the deck is thoroughly shuffled. Well, that's a big if. What they have determined empirically is that if you riffle and shuffle a deck, 7 times, then it is, at that point, completely randomized. That at that point, it can be empirically shown that you will have an equal probability of drawing any randomly chosen card out of the deck. Now, let's talk about the probability of drawing 4 aces. Well, there are how many possible combinations of drawing 5 cards from a deck? There are 52 cards in the deck, and you are going to select 5 of them. That means there are 52 factorial divided by 52 minus 5 factorial times 5 factorial. 52 minus 5 is 47. Yeah. We can take a shortcut here. We go 52 times 51 times 50 times 49 times 48 times 47 times ellipsis, divided by 47 times 46 times ellipsis. Those two cancel out. See what I did? Over 5 times 4 times 3 times 2 times 1. And so even without a factorial button, that becomes something you can do on the calculator. Oh, by the way, in case you're curious, 52 factorial . 8.0658 ... add a bunch more times 10 to the power of 67. From that, divide out 47 factorial . And you're left with 311,875,200 divided by 5 factorial. Which is 120. And you're left with 2,598,960 possible combinations. Oh, look, that is what they get. 2,598,960. Now, what is the probability of drawing the 4 aces? Well, how many combinations of 4 aces are there? There are only 4 aces in the deck, and you're going to use all 4 of them. That means the probability, the number of combinations is 4 factorial divided by 4 minus 4 factorial times 4 factorial. Well, those cancel out, and you're left with 1 over 0 factorial, which by definition is 1. So there's one and only one possible combination of cards that will give you 4 out of 4 aces. There's only one combination that you can draw. But there's a 5th card in your hand. And once you've drawn for those first 4 cards, how many cards are left in the deck? 48. C1 equals 48 factorial divided by what? Yeah, I'm not going to do that. There's 48 of them. Point is that there are 48 more cards, and you can draw any one of them. So once you've drawn the first 4 aces, then there are 48 possible fifth cards you can draw, which means there are 1 times 48 possible combinations of cards that you can draw that will give you 4 aces. Right? So what is now the probability that you will draw 4 aces? Well, there are 48 possible combinations that you can draw out of how many total possible combinations? 2,598,960. What's 48 out of? Well, let me do that. Well, they reduce it to 190. No, they reduce it to 1 in 54,145. Possible. That's the probability that you will draw 4 aces in a randomly dealt hand. 1 chance in 54,000 and change. Now, one more little, I do want to do this next problem before we conclude this chapter and move on to chapter 5. Because I want to cover chapter 5. I don't want to get behind this week because we got an exam at the end of the week on Friday that covers all of chapter 3, chapter 4, and chapter 5. Last chapter, this chapter, and the next one. And what I'm thinking, depending on how well it goes, but I don't want to. I definitely want to take some time this week to answer questions from the homework and work through that as well. So I'm thinking that this exam is probably going to be a take-home exam. All right. That also means there's not going to be any excuse for y'all not to ace it. So. Defective transistors. Let's look at this one. The box contains 24 transistors, 4 of which are defective. If we sell 4 transistors at random, we just randomly select out of that box of 24, what are the following probabilities? Okay, let's see. 24 total transistors. 4 defective. Sell 4. What are the probabilities that A, exactly 2 of them will be defective? Well, we need to know, first of all, how many total possible combinations there are we can sell. And we're going to sell 4. So the total number of combinations is, out of 24 transistors, selling 4 of them will give us 24 factorial divided by 24 minus 4 factorial times 4 factorial, which is 24 factorial over 20 factorial times 4 factorial, which equals 10,626 possible combinations of transistors we can sell out of that box. Now, how many combinations are there where we would sell, where exactly 2 of the ones we chose will be defective. Well, there are 4 defective transistors total. So we would have to choose, first, we would have to choose 2 of those 4 that are defective. And how many possible combinations of those 4 will give us 2 defective ones? 4 factorial over 4 minus 2 is 2 factorial times 2 factorial. That equals, what's 4 factorial? 4 times 3 is 12, times 2 is 24, times 1 is 24, so that's 24. Divided by 2 factorial is 2, and 2 times 2 is 4, so that's 24 divided by 4 is what? 6? There are 6 possible combinations of 2 defective transistors that we can select. If we select 2 defective transistors, how many possible combinations of non-defective transistors can we select? There are 6 possible combinations of defective transistors. Okay? I want y'all to follow me through this thinking one step at a time, because I want you to understand what we're talking about when we talk about these probabilities. Of the 4 there are 4 defective transistors in the box. There are 6 possible combinations of those 4 transistors that we can choose. Now, what about the balance? There are 20 non-defective transistors. And we're going to choose 2 more after we've chosen the first 2. We're going to choose a total of 4. So, we've got 2 more of these that we're going to choose. How many possible combinations of 2 non-defective transistors are there? There are 20 factorial over 18 factorial, that's 20 minus 2 factorial, times 2 factorial. And do you have a factorial button on your calculator? Let me see your calculator here. Yeah, right there. See exclamation point? That's the second function of that. That will give you a factorial. So let's do that. Let's calculate 20 factorial. What do you get? $20 factorial. Read your display. Should be 2.4329, etc., times 10 to the power of 18, correct? That's 20 factorial. Now divide that by 18 factorial. That'll give you 380 over 2 factorial. Well, what's 2 factorial? 2 times 1 is 2. 380 divided by 2 should give you 190. That's the total number of possible combinations of non-defective, that we can pick two non-defective transistors. Now, that means if we've chosen one of these, if we've chosen first two defective transistors, that means that there's 6 possible combinations of two defective transistors we've chosen. For any one of those 6 combinations of two defective transistors, we could then choose another 190 possible combinations of non-defective transistors. So the total possible combinations of exactly two transistors that are defective is 6 times 190, which is 1,140 possible combinations that we can select out of that box, where two and only two of the transistors we select will be defective and 2 will be not defective. Okay. Now, what is the actual probability that we will choose one of those 1,140 possible 1,140 combinations? Think back to probabilities, sample spaces. Remember the definition of a sample space? Here, there are 10,626 possible combinations of 4 transistors that we can select. Okay, we go to a box of 24 transistors, we pick out 4 of them. We have now chosen one of 10,626 possible combinations. Of all of those combinations, 1,140 of them would have resulted in us picking 2 defective transistors and 2 good ones. So our probability of choosing exactly two defectives is 1140 over 10,626. Which reduces, according to the book, down to 190 over 1771. Or if we put that in decimal notation, probability of about 0.107, or about 107 chances in every 1,000. Specifically, 190 chances in every 1,771. Okay, but now here's what I want y'all to think about. Do you understand what this probability actually represents? We've got a box. There are 24 transistors in it. We select 4 of them at random. What is the probability that out of this many possible combinations that we could have selected, we actually chose one of these 1,140 combinations? Okay? Remember the whole thing about complementary probabilities? Do you? Okay. First of all, let's look at this. Look at B. Now that was A, the probability that we would choose one of these 1,140 combinations. That was that probability. What's the next probability they're asking for? What's the probability that we will choose none of them that are defective? Well, we know that there are 10,626 possible combinations. How many combinations would result in no defective transistors? Well, there are, in fact, 20 transistors that are not defective. And we're choosing 4 of them. So how many combinations of non-defective transistors are there? (20 factorial over 20 minus 4 factorial times 4 factorial. That's 20 factorial over 16. Is that right? 20 minus 4 is 16. Factorial times 4 factorial. And if you do the math, according to them, it works out to 4,845. 4,845 possible combinations of those 20 transistors. So, of all 24 transistors, there are 10,626 possible combinations. But only 4,845 of those combinations have 0 defective transistors in them. So the probability of choosing four transistors at random with no defective transistors are 4,845 chances in 10,626 possible combinations, which, according to the book, reduces to 1615 over 3542. Or we could write that as in decimal notation as approximately 4845 divided by 100626, or approximately 0.456, 0.455957086, etc. Or approximately 456 chances in 1,000. So a little less than half the time you would get 4 good transistors. Now what are the odds that you would give them by randomly selecting 4 transistors? You give them all 4 of the defective. Well, how many possible combinations of 4 defective transistors are there? No. Of the 4 that's how many possible combinations there are of all 24. Of the 4 defective transistors, how many combinations of those 4 will result in all 4 of them? Out of 4 defective transistors, you're choosing 4 of them number of combinations, how many combinations of all four of them can you arrange in a set of four? It becomes 4 factorial over 4 minus 4 factorial times 4 factorial. Those cancel. 0 factorial, which is defined as 1. So that's 1. There is only one possible combination of all 4 defective transistors as a set of 4. That is the only combination that will give you all 4 defective transistors. But there are 10,626 possible combinations that you could choose. So what's the probability that you would choose that one and only one combination? One chance in 10,626 that you would give them all 4 defective transistors. Now, what is the probability that you would give them at least one defective transistor? Now, maybe you'll give them 2, maybe you'll give them 3, maybe you'll give them all 4. But what's the probability that you would give them at least one? Well, the first thing you'd have to do is calculate the total number of, well, we already calculated that there's only one combination that you would give them all 4. Then you would have to go in and calculate how many combinations of 3 could you get out of those 4. And then calculate how many combinations of 2 could you get out of those 4. And then how many combinations of 1 could you get out of those 4? Then you'd have to calculate all of those probabilities and the probability that all 4 of those would happen, or if that any one of those 4 would happen. Or we can go back and use that complementary rule of probabilities. Instead of going through and doing all of those calculations, calculate all of those different probabilities, let's calculate instead the probability that you would not give them any defective transistors. Well, how many combinations of 0 defective transistors were there? Of the 10,626 possible combinations, there are 20 that are not defective, and you're going to choose 4 of them. So that gives you 20 factorial divided by 16 factorial times 4 factorial. And didn't we just do that one a minute ago? No, we did 20, we did 2, not 4. Okay, well, what does this work out to? Jordan, what do you get with that? Start with 20 factorial. 2.43, etc., times 10 to the 18, right? Okay, now divide that by 16 factorial. $116,280. And now divide that by 4 factorial. Which is 24. What do you get? You get 48, 45? Okay. That means of the 10,626 possible, possible combinations, 4,845 of those combinations would result in no defective transistors being selected. So the probability of no defective transistors is then 48, 45 divided by 10,626. That is the probability of 0 defective transistors. Now, all you need to do is find the complement of that. Because if you did not sell them 0 defective transistors, then you had to have sold them at least 1 defective transistor. See how that works? This is where that complementary rule comes in. So the probability of at least 1 is the complement of the probability of 0, which is 1 minus 4845 over 10,626. And look, let me show you here just a little bit. We can do some simple algebra here. That becomes 10,626 over 10,626 minus 4845 over 10,626, which is 10,626 minus 4845 divided by 10,626. What's 10,626 minus 4845? $5,781 out of 10,626 is the probability that you will sell them at least 1 defective transistor over half the time. If there are only 4 defective transistors and you pick out 4 of them, over half the time you're going to get at least 1 of the defective ones. Okay? But did you see what's happening here? This is basically the complementary rule, just taking it out and apply. If there are this many chances of no defective transistors, this many combinations will have 0 defective transistors, then the total possibility minus that is the number of combinations that will have at least 1. Okay, I don't want to keep beating a dead horse, but I do want to make sure y'all understand what we just did here. Okay. Then, and that's the end of the day. So we will pick up on Wednesday with chapter 5, and I guess that means we will definitely be doing a take-home test on Friday. Because I'm not going to try and squeeze in all 3 sections of 5 on Wednesday and try to answer homework questions. So do either of you have a homework assignment ready to turn in? Okay. Well, if y'all need help, you know where my office is. And I will see you on Wednesday. Be ready with questions from the homework. And not just last week's homework that's due now, but this week's as well.